Okay, good morning once again, and I want to welcome you to my lecture today. Today, uh, October 26, 2020, I'm actually going to be walking you through another exciting topic in statistics. And of course, basically, what we want to do today, we're actually going to have an extensive review on additional topics in regression because we're going to start a new chapter on Friday. I mean, we're going to start a new chapter on Wednesday. Okay. Now we want to review, some important things in multiple linear regression. You're also going to have a new thing. You're going to have something new today as well. Okay. So give me 1 second. I'm actually gonna be with you. Okay. So like I said in the outline, I'm going to talk about assessing a multiple regression model. I'm going to talk about the confidence interval for a multiple regression coefficient. I'm also going to talk about the ANOVA for multiple regression model. Then I'm going to talk about multicollinearity. Okay. Now, uh, let's get started with assessing a multiple uh, linear regression model. Okay. Now, in multiple linear regression model, of course, it means I'm interested in investigating more than one predictor at a time, on the response. Okay. Now, if I want to do that, I'm actually going to have the estimate, of the parameters associated, uh, you know, of the estimate of the parameters associated with that correspond to the predictors. Not only that, I'm actually going to have a standard error correspond to that will enable me to test, the significance of each parameter and stuff among other stuff. Okay, um, you know that if you do that in R, you're actually gonna get the estimate of parameters, right? The estimate that you normally have are single values. Okay, they are point estimates, and of course, we can actually find the interval estimates for each parameter, just like what we did in the simple linear regression model. And of course, this is if I actually want to do that, this is the formula that I'm actually going to use. Take a look at that formula. Okay, if I have a beta cap 1, of course, that's going to be plus or minus the margin of error. The margin of error there is just the t-value multiplied by the standard error. And of course, how am I going to achieve this in R? Of course, I'm actually going to show you the code, okay, if you want to get that in R. Okay, so if that is what I have, I'm actually want to uh, use an example right now. This example is actually going to come from NFL winning percentage. Okay, the NFL winning percentage, uh, where we actually want to investigate what is important between the offense and defense. Okay, uh, in winning football games. I'm so sorry that right now some of you are really missing football activity due to pandemic, but I can assure you that everything will soon return to normal, where you're going to have opportunity to meet out with your friends and you watch a football game that you like. Okay, so in winning a football game, okay, what is more important? Is it the offense or defense? And of course, you know, if we want to investigate this, we're going to be making use of the NFL data, 2007 regular season. Now, this is the code. Can you guys confirm if you're seeing the code right now that I'm actually projecting? Can you see that? Okay, thanks for confirming that you are seeing the code. Now take a look at what I have right now. Um, if you take a look at the variables in this data, we got team, we got conference, because of course there are different conference in the United States. Okay, in terms of when you are talking about football league, they get division, then wins, loses, win percentage, point for, point against, net points, and so on like that. Okay, so what I'm trying to show you right now is more or less the data layout. Okay, right now I'm only showing three teams: the New England Patriots, Dallas Cowboys, Green Bay Packers, you know, and I'm trying to show that over some variables. They are more than that, okay? They are more than that. I just decided to show the first three teams. Now, what am I looking at? I actually want to investigate. Some of you that may want to write projects on this. Uh, you know, this is a very good area to write project upon. I told you before, the fact that you've submitted practical one or practical two, that doesn't mean you cannot change your mind. You can still change your mind. And when you change your mind, you are not going to lose anything. And let me confirm to you today. I'm going to confirm to you today, and I'm going to send a message to my TA as well. What have a deadline? Other deadlines are flexible, but the one that is not flexible is a final deadline, the one for practical three. And of course, some of you have been asking me question about the guideline for practical two. I think I said that in practical one, that you only need to show your data. That's all. In practical two, you need to import your data into the practical two port. That's all. That's it more. The moment you show your data, that's all. You're going to have your full grade for practical two. Okay, because we are trying to investigate um, which one is important between defense and offense in winning percentage. Okay, we're talking about football game. Now, because of that, we're actually going to look at the effect of point for, then point against on the win percentage. Take a look at that. And this is a multiple linear regression, because of the fact that the number of predictor here is more than one. I think you know that. Okay, so after running that, take a look at what I have now. That is actually the result. Can you see that now? That is the arrow output. And of course, in the arrow output, this is the estimate of the parameters. Can you see that now? And of course, this is the standard error associated with the estimate. And of course, that is a t-value in case you want to test the significance of each parameter in this model. And of course, to take your decision, of course, you actually need to use the p-value associated with that. And take a look at that. The variable considered here, each of that are significant because the p-value is actually less than 0.05. Okay, so if that is the case, uh, we actually, and of course, you can see right here, what is telling us the significance of the overall parameters in the model. You can see that. And that is also telling us that the variables are linearly related, and then the linear relationship here is statistically significant because the p-value is less than 0.05. And of course, you can also see here the multiple R squared, 88.44%. So which is giving an indication of a good model. But there is something that is mixing right here, because if you look at this guy here, we're talking about the estimate of the parameters, and of course, you have a single value for each of that. And you know what? A single value could be wrong or right according to the classical approach of probability. And so this is what we call point estimate. And because of that, because of the fact that a single value could be wrong or right, then we're actually going to consider what we call the interval estimation. Okay, and if I want to get the interval estimation, this is the code that I'm actually going to write. That's going to be confit. Then reg, of course, don't forget the other time, reg is what I use to save my model with. I'm going to show you right now. Take a look at that. I use reg, that is a name that I use in saving my model, when running that. And of course, if you take a look at that right now, so this is a code. If I want to get a confidence interval, why do I specify 0.95? Because I want to do 95% confidence. Okay. If I want to do 90% confident, I'm actually going to indicate 0.90. If I want to do 99% confidence, I'm actually going to, put 0.99. And at the end of the day, this is the way the result is actually going to come out. Okay, we are not going to have a single estimate for intercept. What we're going to say that, okay, uh, the true value of of that parameter actually lies in that interval. Of course, the fact remain that the interval will always contain the true value. Okay, so you're going to have that for the intercept, for the point four, and for the point against. Okay, so what I'm just showing you right now is a confidence interval for a multiple regression coefficient in R. Okay, and that is the way it's actually going to be presented. Can you guys still hear me? Okay, so thanks for confirming that. Now, the next thing that is actually going to be new today, that I said is going to be new, is what we call multicollinearity. And let me tell you this: one important assumptions of the important assumptions of multiple linear regression is multicollinearity. Okay, in addition to assumptions of linearity, in addition to assumptions of constant variance, and so on like that, multiple linear regression, actually we have an assumptions of multicollinearity. And what do we actually mean by multicollinearity? Multicollinearity means, variables, predictor variables that are correlating. Okay, when predictors variable correlates, that could be problematic to a model. Okay, and that is the reason why I'm actually going to walk you through how you can identify multicollinearity in regression, and how you can also understand the effect of multicollinearity on multiple regression models. And you know what, like I said, uh, uh, multicollinearity could be problematic to model in such a way that when it is present in a model, of course, it's actually going to cause a damage. And what kind of damage? The kind of damage is just that when predictors are known to be significant, because before you go into statistical analysis, of course, you understand the basis, like uh, maybe uh, we only have what we call expectation, that okay, for instance, take a look at, if I'm looking at the relationship between spending and saving, then I know that the sign, if I'm actually going to use saving as a predictor, then the coefficient, you know, for savings should be negative. But when multicollinearity exists, you know what? When the multicollinearity exists, it's actually going to switch the sign. It's not going to be negative, maybe it could be positive. So, which means one of the problem created by multicollinearity is that it could switch the signs of the regression coefficient, and not only that, it's actually going to make you know pre, predictor that's supposed to be significant is actually going to make them insignificant. Okay, and why are they going to be insignificant? Because it's actually going to increase the variance of this coefficient. And of course, when the variance of the coefficient uh, is increased, then the standard error of the coefficient is actually going to increase. And when the standard error of the coefficient increase, of course, the t value is actually going to be small. And when t value is small, the p value associated with a small t value will be large. And when p value is large, then you are not going to reject the non-hypothesis. And when you don't reject the non-hypothesis, then it's trying to say that you know uh, your coefficient, your the parameter is not significant. I think I saw something on my chart right now. I'm actually going to read that. Somebody said, could you talk a bit more about what is correct model? Uh, okay, this is what happened. If you are really talking about this guy here, okay, uh, uh, what I'm trying to talk about is just that the situation whereby multicollinearity exists, then you don't expect the model, the coefficient estimate to be stable, which means we can't rely on, let me walk you back. You can't rely on, you can't rely on this. You can't rely on the result you are having there. Okay. So which means the coefficient, the result you are getting is unstable, because of the fact that there's multicollinearity. Okay. So, and that is the reason why I said here that, let me read that. I said the result is that the coefficient estimates are unstable and difficult to interpret. And multicollinearity can cause the coefficient to switch signs, which I said, and make it more difficult to specify the correct model. So it means, actually, that should be model, okay? Now, which means if the multicollinearity exists, it may be difficult for you, which means your model may not be correct. The model you specify may not be correct until the only thing you just need to do uh, the only thing you need to do is you need to first correct for that model. You need to adjust the model. You need to, correct for that multicollinearity before you can have your model stable. Otherwise, whatever decision you're going to take with the model will not be valid. Did you get that? Okay. Now, what I want to do now, I'm actually want to show you how you can investigate multicollinearity, okay, in statistical analysis, okay? And you know what? Multicollinearity could be exact, could be severe or, you know, it could be moderate, okay? So if I want to investigate multicollinearity, I actually need to load a package called Faraway, okay, now. And after doing that, now I want to use different variable now. If you take a look at the data, if you take a look at the NFL that I was talking about before, we did not actually uh, suspect multicollinearity here, okay? But we can still investigate. But I want to use a different data now, okay? And in the different data that I want to use, these are the variables. I got age, I got weight, the height of shoes, okay, and so on like that. The predictor variable is if center, okay. The predictor variable is if center. And what am I trying to do right here? I'm trying to get a correlation. Look at code. I'm trying to get a correlation of all the variables. Why am I trying to get a correlation of all the variables? I'm trying to get a correlation of all the variable because I know that multicollinearity is when uh, you know variables are having correlation. I mean, are having relationship. They are correlated. Okay, and that is the reason why I'm trying to obtain the correlation of value. Correlation for any pairs of the variable. And of course, you can actually see some I values. You can see that some of the variables have high correlation values. You can see that now. But this is necessary but not sufficient to properly investigate. But you know what? If you properly want to investigate, you know what I'm actually going to do? Let us try and look at the effect. Let's run a regression where we want to look at the effect of age, weight, height of shoe, height, seated arm, uh, thigh, leg on the hip center. Now, what can you see? None of the predictor is significant. Can you see that? That is interesting. It is only the intercept that is significant here. And of course, there should be a connection. We know before we go into statistical analysis that any or each of these, at least some of these predictors must be significant. They must have a connection to the response, because nobody goes into research with an empty mind. There's nobody that go into research. You remember the other time that what we specified as a model is as a result of what we have in mind. Okay, and you know what? If you're doing economic analysis, if you want to apply statistics into economic theory, of course you know there's an economic theory. Okay, and then if you want to apply statistics into sociological, maybe in sociology, in psychology, of course you have a background information. You know your relationship. You have expectation even before you go into statistical analysis. But take a look at this. From your expectation, you expect that at least one of these predictors should be significant. But based on what I'm seeing right now, none of them is significant. And there's another thing I want you to see. Take a look at this. The F test, the p-value associated with F test is telling us everything is good, everything is fine, because the p-value here is less than 0.05, which is giving an indication that everything is fine. But you know what? But if you look at the t value, if you look at the p-value associated with each of these, predictor, the p-value is actually greater than 0.05, which means none of that is significant. Therefore, there's a conflict. Therefore, we need to investigate for multicollinearity. Okay? We actually need to investigate because when multicollinearity is present, of course, a variable that's supposed to be significant will not be significant. Okay? And not only that, it's actually going to switch the signs, because there's something I'm actually seeing right now. And that is why I put my observation like this. I said, one of the first things we should notice is that the F test for the regression tell us regression is significant. However, each individual predictor is not. That's what I just showed you right now. And another interesting result is the opposite signs of the coefficient for HT, okay, and HT shows. And this should seem rather counterintuitive. Increasing HT increases ipsena, but increasing HOs decreases ipsena. That shouldn't, now if you go back, look at that. It's negative. Can you see what I'm talking about? And this guy is positive. Can you see that now? So that is kind of conflicting. So those are the things that you're actually going to see in the regression model that you may be suspecting multicollinearity. Okay, now, and I said this happened as a result of the predictors being highly correlated. For example, the HT show variable as explain a large amount of variation in HT. Okay, so when you look at the these two variables, they are highly correlating, and that is the reason why there's a problem. Okay, now if that is the case, we're going to be thinking of what to remove. But you know what? I'm actually going to, like I said, looking at the correlation value is not a sufficient way to decide on multicollinearity. But what is the standard way? What am I actually going to do? What you're actually going to do, you need to investigate the VIF. Okay, the VIF is what we call variance inflation factor. And of course, the formula for VIF is this guy here. And of course, It is 1 divided by 1 minus rj squared. The rj squared, of course, is a multiple determination. Okay. Now, the multiple determination between probably any pairs of the variable. But you know what? We got a way to do that in R. If you want to do this in R, this is what you're going to do. VIF, take a look at that, because I saved my model with IP model. If I take you back, okay, I'm going to take you back right now. You're going to see, take a look at that. I'm saving that with IP model. Can you see that now? Then after running my regression, then I'm going to do VIF of whatever I save my model with. Okay. And after doing that, the next thing I'm actually going to do, take a look at that now. I'm actually going to have access to the VIF of all the models. I'm actually going to have access to the VIF of all the models. Take a look at that. I have access to the VIF of all the models. And you know what? I'm actually going to remove predictors whose VIF value is greater than 5. That is the threshold that we're actually using. Though some statisticians argue that it should be greater than 10, some statisticians argue it should be greater than 5, but I belong to the group of statisticians that actually believe we should be using a threshold of 5. Okay, there's a good number of statisticians who believe that the predictors whose values of VIF greater than 5 should actually be removed. Now, if I want to talk about the one that are greater than 5, I'm actually going to be talking about this guy here. But you know what? Because of the fact that uh, uh, before going into the analysis, there's a connection between the height of the shoe, between the height and the hip center. Now, because of that, I'm going to drop only one of these. Okay, I'm not going to drop these two. Okay, I'm only going to drop only one. Okay, now let us now see. Like I said, I'm dropping this guy, I'm dropping that guy, and of course, I'm actually going to drop only one of that. Okay, now take a look at this right now. If I drop that now, I'm actually going to rerun my regression. Uh, Give me 1 second. I'm going to. Okay, take a look at that. After dropping that, this is what I have. Okay. Uh, right now, I'm only considering age, arm, and HT. Look at that. Those are the 3 variables that I'm considering right now. I've already dropped some, though HT also have uh, VIF greater than 5, but because it has theoretical backing, that it should be included in the model, because the reason why it was having issue before is because of the fact that H tissues was correlating with it. Now take a look at what we have now. Uh, one of the predictor variable is now significant. You remember before it was not significant, but take a look at that now. Somebody said, could we have picked either of them and been fine as long as there's only one? Yes, because it's more or less like having two captain in a ship. When you have two captain in a ship, it's going to do a damage to the ship. Okay, and that is the reason. It means the two captain, they're going to be dragging stuff, and there's actually going to be a problem. The ship could be submerged. You understand what I mean? Okay. So when two variables are actually correlating, okay, uh, and then if one of them has theoretical backing because of course the height should have effect on the hip center. We're talking about hip center height even before running statistical analysis. We know that it should be significant. So the reason why it was not significant before is because of the fact that you know uh, because of the fact that there was a variable correlating with that, and that variable had been removed. Now, take a look at what I have now. Everything is looking so good, but you know what? You can actually investigate again, okay? For you to be sure, you can find the VIF again, okay? Now, when you find the VIF again, take a look at what I'm having right now. None of that. Can you see now? None of that is less than 5. None of the H, the ham, and the HT that we tolerated in the model. None of them is less than 5. Take a look at that. And initially, you remember the other time? You remember that um, the, what is it called? You remember that HT was having a very high VIF value before. But now, the reason why it was having a high VIF value is actually because of the fact that there was a variable called H2 shoe that was correlating with it, and that had been discarded. Now, take a look at what I have now. Everything is looking so good. And you know what? Uh, you can actually use the idea of what we have done before to compare the two models. The model, the model we fitted before that have up or predictors, and the one we just fitted now that have just 3 predictors. And of course, if we want to test statistically, though we have been able to see there's no problem anymore, no problem of multicollinearity, but do you know that you can actually test which of the two models is fine? And if you want to do that, you're going to use a partial F test. Do you remember the idea behind the partial F test? I need you to confirm if you remember the partial F test that we did. I need you guys to comment right now whether yes or no. Do you remember the partial F test that we did before? Okay, if you remember partial F test, we normally use partial F test in situation whereby we got two models, a very simple model and a complicated model in such a way that the simple model is actually nested a complicated model. Of course, and remember model 1, this is a simple model after controlling for multicollinearity. And take a look at this guy, model 2 is a complicated model when we have not control for multicollinearity. Now, when we carried out a test, this is under the non-hypothesis, and the second model is under the alternative. Now, take a look, don't forget that I said you're going to do ANOVA, right? You're going to do ANOVA for each of the model, you remember? This is for the smaller model, the simpler model, and for the complicated model, okay? Now, when you do ANOVA for that, you're actually going to have the result that I'm showing you right now. And take a look at this guy. This is a p-value. The p-value right here is greater than 0.05, and which means you're actually going to fail to reject. Okay? You're going to fail to reject the non-hypothesis. What does that imply? Of course, that implies that the model 1 is better. Look at that. The model 1 is the model that we have already controlled. We have been able, to address the multicollinearity issue. So which means what could make model to be problematic at times could be as a result of the presence of multicollinearity. Is there anyone who want to ask question right here? Is there anyone who need clarification? Are you guys still hearing me? I need you guys to confirm if you guys are hearing me now. Oh, okay. Some people say, like I said, do not hide your feelings. If you don't understand, let me know. Okay, so therefore, that is what we actually you know have. Now I want to go into another example right now, and this time around in the example I want to consider give me 1 second. Okay, now another thing I want to talk about: how do we fix a multicollinearity problem? Okay, uh the one we just did is the second one, by removing highly correlated predictors. Okay, of course, you know how we remove that right now. We try to find the VIF, and then we remove predictors whose values is whose VIF value is greater than 5. Okay, but you know what, it's not all the time that we actually going to remove. Okay, because situations whereby maybe predictors are significant, okay, then we cannot remove. Maybe when we run the initial regression and predictors are significant, we cannot remove. Maybe the only issue that we may have, maybe there was just a switch in sign. And what can we do in that situation? We're actually going to standardize our predictors. And I'm actually going to walk you through that example on how you can standardize. Okay, now take a look at this example uh, right now. Now, looking at this example, I want to look at the effects of fat, weight, and activity, and the interaction between fat and weight on the femoral neck. I run a regression, I got the output, and I try to get a VIF. Can you guys see the VIF right now? If you take a look at this VIF, you're actually going to see, let me just interpret, let me see what is happening here. What is happening here, uh, weight is significant. Take a look at that. Activity is significant. The interaction between fat and weight are significant. But there's something I wanted to see. Interaction between fat and weight are significant, but fat itself is not significant. Okay, take a look at that. Interaction between fat and weight is significant, but fat separately is not. Okay, fat is not. Then uh, nobody knows. You know, there could be a problem here. And that is the reason, take a look at the VIF. We find the VIF, and the VIF associated with fat is 14.9316, and that is greater than 5. Look at the one associated with weight as well. Look at the one associated with the interaction. What are we going to do here? What we're going to do here, we cannot discard predictors whose the VIF is less than 5. We cannot. The only thing that can be done in this situation, we actually need to standardize predictors. How can we standardize predictors? Okay, the predictor here is fat, weight, and activity. Of course, we have the interaction between fat and weight. If I call this guy X1 and I call this guy X2 and I call this guy X3, okay, and I call this guy here X4. Of course, X4 is the product of X1 and X2. I think you know that. Now, if I want to standardize, of course, I need to get Z1, Zi will be equal to Xi minus mu I divided by sigma I. Of course, you know how to get a Z-score, right? So it means for each of these predictor, you need to find the mean of each predictor that you're going to be subtracting, okay? And after subtracting, you're going to be dividing each of the data point by the standard deviation. Then you're going to have a Z1, you're going to have a Z2, you're going to have a Z3, you're going to have a Z4. Those are standardized values of predictors that you're actually going to have. My TA will walk you through this in the lab. But you know what? After standardizing, then you're going to rerun your regression. Okay? You're going to rerun your regression. And I'm actually going to show you now. Take a look at that. After standardizing, rerunning your regression, finding a VIF, look at what we have. None of the VIF is greater than 5 anymore. Are you guys still hearing me? Okay. Now, none of the VIF is greater than 5 anymore. And another thing you're going to pay attention to, facts that was not significant before is now significant, because there is no way interaction will be significant and the part of the component in the interaction will not be significant. There's no way. And look at what is happening now. After correcting that, the fact is now significant. Take a look at that. The p-value is less than 0.05. Everything looks good right now. Take a look at that. And of course, look at the VIF. Like I said, when you had, after, intervention, you actually need to compute your VIF again. Okay. And when you look at the VIF, none of that is greater than 5. Like I said, the threshold that we're using is right here. Take a look at that. I said, however, 3 of the VIF are very high because they are well over 5. And this value suggests that the coefficients are poorly estimated, and we should be wary of their p-values. The one I'm referring to, the one we computed before. This guy here. Okay. And why do we suspect multicollinearity? Because of the fact that the interaction between fat and weight is significant, but fat itself is not. Take a look at that. And that created suspicion in the first place. And of course, when we have a suspicion like that, then we need to be able to investigate the VIF. And look at the VIF, of course, you can see the VIF, some of that, are actually over 5. And if they are over 5, I'm not going to discard, I'm not going to remove any predictors right here. I'm not going to remove any predictor. Why am I not going to remove any predictor? Because look at it, some of them are significant. Some of them are significant. I can't remove them. Okay? And the only thing I can do in this situation under which I cannot remove, is when we realize that some of the predators are even significant. And the only thing that can be done is to standardize. Okay? And after standardizing, and of course you can see what we have. When we have after standard, and that was why I call that regression with standardized predictors, because I'm no longer using the original values of the predictors. We have already standardized that, and standardization is one of the transformational efforts when there's a crisis. Okay, now you can see that now everything is so good. Okay, before I go, I'm actually gonna quickly talk about something. There is something that I actually put right here that I did not talk about. Uh, in the example that I was using before about the shoe age and whatever, if we want to investigate how the presence of collinearity actually affects a model, if we had a moderate amount of noise to the data, adding a noise to the data, we don't expect that to change anything, because a noise is not something that we expect that should be significant. Okay. Now, let us see let us see whether the estimate is going to change. Now, take a look at what I have before. Give me 1 second. Um, give me 1 second. I'm going to. Now, the coefficient that we have before. Yeah, these are the coefficients that I have before, right? Those are the estimates that I have before, right? Now, when we decide to add noise, into the model. Okay, that is a code to write to simulate noise into the model. Take a look at that. I'm adding noise. Okay, now adding noise into the model, and I'm trying to investigate. Look at the coefficient now. You can see the coefficient compared to uh, the way it was. I'm gonna age is 0.7757 here, and let's go back. Let's see what is gonna be here. Okay, it's still 0.77. So we want to see whether there's going to be a kind of change. Now let us look at the weight. The weight is 0.02, right? 263. Okay, it is also 0.0263. Let's look at the um, age tissues, minus 2.69. Okay, it's still minus 2.69. Let's look at the okay, let me see what I'm trying to. This is for HP model. Let me see what I use to save with that one. Okay, now this is what I was saying. This is what I was saying. Take a compare this to what we have now to this. They are not the same, right? Now that means there's a drastic. Now, what I want you to see is this. After adding a noise, let me just say this is what I have now. After adding a noise, okay, and without noise, look at that. This is what I have. This is what I want us to compare. Without noise, look at that. I want you guys to pay attention and see now. Now, use your mind. Just go through that now. Can you see that now? Now, after adding noise, let's see what we're going to have. Look at that. Intercept is 424, but initially it was 436, right? Age is 0.7757, but now it's 0.6897. Can you see now? There's a difference. And if we had a noise into a model, we don't expect a drastic change in the parameters. But do you know the reason why there's a drastic change here? Because of the fact that there's a problem of multicollinearity. And that was why there's a drastic change. Okay? And, and that was why I said this tells us that a model with collinearity is bad at explaining the relationship between the response and the predictors. We cannot even be confident in the direction of the relationship. Direction means the sign, because it could be positive and it's actually going to give you a negative. It could be negative, it's going to give you a positive. So, however, you know, does collinearity affect prediction? Okay, so that is that. So, what I've explained to you today, I think I've been able to explain the how you can investigate multicollinearity, the damage it does to the model, how you can correct that, and you know, what that you can do. Okay, and we have different ways to correct for multicollinearity. Now, is there anyone who want to ask question before I go today? Because on Wednesday we're actually going to start a new topic, a new chapter, chapter 5, that I'm actually going to call analysis of variance. That is going to be the focus on Wednesday. Is there anyone who want to ask question before I go today? Is there anyone? Are you guys hearing me clearly? Okay, so is there anyone who need clarification? Does that mean now you guys know how to investigate multicollinearity in a multiple linear regression model? Does that mean you know how to do that? Okay, now you know the threshold, you know when we discard predictors, and when you know when we standardize. It's not all the time that we discard predictors. Now, in the absence of question, I want to thank everyone who have attended my lecture today. I hope you guys enjoyed this lecture. Make sure you guys stay safe and have a good day. Bye for now, guys. Yeah, thank you too. Thank you, guys.